the second example, what we have is a container like this, and then for example you would measure some liquid or any sample in your lab. You first put the container and then it will show the mass, and then add some liquid, it will show the total mass. Let us say the balance now shows the weight, then it first show the weight of the container and then the weight of the container and liquid. Now what we have is opening there at the top, and then liquid flows down into the container and leaves through the sides. Now the reading shown by the balance will be different, it will account for the momentum of the liquid entering. So that is what we are going to see now in this example more formally. Let us read the example. A metal container 0.6 meters high, that is a total height of the container, with an inside cross section area of 0.1 meter squared, weighs 2 kg when empty. So this is something like putting your beaker and then weighing, and the container is placed on a scale and water flows in through an opening in the top, that is shown here, and out through the two equal area openings in the sides, as shown in the diagram. Under steady flow conditions, the height of the water in the tank is 0.5 meters. So that indirectly gives us the volume of water in the tank. You are given the area of the inlet and the two outlets, okay, all of them have the same area. We are also given the velocity, and look at the way in which it has been given. The velocity vector is given, it is flowing downwards, so it has only one component Vy, and because it is towards the negative y axis, it is -3 and then j, okay. And so magnitude of velocity is 3, and along this direction it is -3j. Will the scale indicate weight of water in the tank plus tank weight? If not, what is the reading on the scale? Okay. Now the control volume is shown here, or surrounded by the control surface, and mass enters and leaves through the control surface. In terms of momentum, this contributes towards the y direction, and these two flows contribute towards the x direction. Since we are interested in the reading shown by the balance, we are interested only in the y momentum balance, which means only this flow will be contributing. Now we denote Ry, which is taken as positive along the y axis, as the force of the scale on the control volume. Okay. As the previous example, we should be careful of the direction of force exerted by the scale on the control volume, okay, and of course through the supports, and it is assumed positive along the y axis. We have taken Ry to be directed along the positive y axis, okay, assumed positive along positive y axis. Now W tank denotes the weight of tank, okay, and it is towards the negative y axis, which you already know. Similarly, W water represents weight of water in the tank, that is also along negative y axis, okay. And atmospheric pressure acts uniformly on the entire control surface, and hence exerts no net force on the control volume, okay. If you have any object and then it is subjected to atmospheric pressure, there is no net force acting on the object or the control volume, okay, be it any shape. This particular, even if it is a regular shape like a cuboid or a shape like this or any shape like this, if it is just subject to atmospheric pressure, there is no net force acting on it, okay. That also we can intuitively understand. Okay. So with all this information, we will proceed further. We will start with the integral momentum balance in the y direction, because we are interested in the force of the balance on the control volume. Okay. So that is the integral balance equation in the y direction. That is why we have used the y component of velocity here. Similarly, here y component of velocity. Okay. So, this tells you that rate of change of y momentum in the control volume. This term tells you net rate at which y momentum leaves the control volume, body forces, surface forces acting along the y direction. Now, we will consider steady state condition. What does it mean? The level in the tank does not change with time, and hence we say it is under steady state condition. Okay. Remember, if you recall the experiment which we have done, we had two inlets. Okay. We had two inlets in an experimental setup and then one outlet. Okay. And here again, when we took the data, we made sure that the level in the tank remained constant. If it is changing, then it is under transient condition, but we make sure that this flow is equal to sum of these two flows and the level does not change with time. So, the first term drops out, this transient term drops out. Now, I am left only with the convection term and the force term on the right hand side. Now, let us call V 1 as a magnitude of y velocity, and so the V vector has only one component, the vertical component V y, and then of course, in vectorial notation V y j, and V 1 is a magnitude. So, V y becomes minus V 1 j vector. Okay. So, velocity vector is in terms of the component y, V y is a component of velocity, but V 1 is a magnitude. So, we write as minus V 1 j. Now, let us compute this convective momentum term, and as I told you, the momentum flow which contributes along the y direction is only this flow. Okay. Other two flows are in the horizontal direction. So, they do not contribute to momentum in the y direction balance. So, that is why control surface is replaced with CS 1. If it were mass balance, then you have to consider CS 2, CS 3, control surface 2 and 3, but because it is momentum balance, we consider only the control surface 1, which alone flow through, that alone contributes to the y momentum. Okay. So, now let us substitute. Of course, I assume this to be uniform throughout the cross section area, that is why I have A 1 here after integrating. I have written rho here. The y component of velocity is minus V 1, the velocity vector V is minus V 1 j, the n vector, this is an inflow, our normal is always away from the control volume. So, it is in this direction, which means along the positive y axis, and hence it is j vector. So, if you simplify, you get rho V 1 squared A 1, and of course, it is positive because V dot n is negative, it is an inflow, V y is also negative. So, resulting in a positive sign for this rate of momentum term. Now, coming to the gravity vector, the gravity vector has only one component here once again, the component of gravity along y direction is g y along with the vector j. If you write in terms of magnitude, g is 9.81, that is the value, and because it is along negative y axis, it is minus 9.81 j. Now, let us write the body force along the y direction. What is the body force along the y direction? Is mass into the component of gravity along y direction. So, if you write here, there are two components to it. One is the mass of the tank multiplied by minus g, then you have mass of water in the tank multiplied by minus g. So, if you simplify, you get the sum of both the masses into the g. Remember, g here is just 9.81, we have taken care of negative sign here because it acts towards the negative y axis. And the surface force is R y, which is along the positive y axis, and we already discussed that there is no net force due to atmospheric pressure. Okay. Now, let us substitute all the expressions in the integral momentum balance along the y direction. We found out the convective term, convective momentum to be rho V1 squared A1, and the body force as the sum of mass of tank and water multiplied by g with a negative sign, surface force as Ry. So, let us substitute as usual with the convective momentum on the left hand side, the forces on the right hand side, and then rearrange for Ry. Ry is the force of the balance on the control volume or the reading in terms of force of the balance. Okay. Now, mass of the water in the tank is not given directly to us, it is given in terms of the level of water in the tank, that is H multiplied by the cross sectional area of the tank, that gives the volume, multiplied by the density of water gives you mass of water in the tank. So, that is how you get mass of the water in the tank. Mass of the tank is given to you directly. So, m tank plus area of the cross section area of the tank multiplied by H multiplied by rho water g plus rho V1 squared A1. Okay. So, scale reading is the tank weight plus water weight plus downward momentum of entering fluid, that is extra term which you have taken into account. These two terms are very well familiar to us. What is the extra term based on this example is that the downward momentum of entering fluid. Okay, let us substitute the values given in the problem. So, the mass of the tank was given as 2 kgs, cross sectional area was given as 0.1, height was 0.5, total height was 0.6, height to which water is present under steady state condition is 0.5, density of water 1000, acceleration due to gravity 9.81, density of water 1000, the inlet velocity was given as 3 meters per second, it's a high velocity, very high velocity, okay, especially for water, and then area was 0.01. Okay. So, if you substitute you get a nice number of 600 Newton. It has two components to it, that is why specifically the steps are shown in terms of components. One component is because of the weight of the tank and the water, other component is because of the momentum. Okay. So, if you are neglecting momentum, then we would conclude, I would say wrongly, as 510 Newton, but the balance would show 600 Newton taking into account the momentum of entering fluid. Okay. So, force off scale on the control volume, which is the reading of the scale. So, to answer the question, scale will not indicate weight of water in the tank plus tank weight, that was the question, whether will it indicate that. So, it will not indicate 510 Newton only. Momentum of flow contributes 90 by 600, 15% of the to the scale reading. Okay. That is why this particular example, the velocity is chosen to be a very high value. For 3 meters per second for water is a very high value. To really emphasize the point that momentum can contribute, a high number is chosen. If you choose a low velocity, then of course this contribution becomes lower and lower. Just to emphasize that it contributes up to 15%, a really large velocity has been chosen. Okay. So, only takeaway from this example is that the momentum of water entering also contributes to the scale reading. Okay. And it is also a good problem solving practice that till the last step we work in terms of variables and then substitute in the last step. This avoids numerical mistakes. Apart from that, you have a very general expression which is valid for this any value of the variables. If you start substituting in the beginning, that becomes very specific for that example. So, any configuration of this you can this expression is valid. For example, we are discussing that if the velocity becomes smaller and smaller, you can see that this contributions contribution becomes lower and lower. So, for example, you can try with 1 meter per second or 0.5 meter per second, this becomes smaller and smaller, that also it is squared. Okay. The next example is flow through a elbow, which is a usual pipe joint for connecting two pipes, and here it is a reducing elbow because you have a larger cross section here and a smaller cross section here. And usually we attach this elbow to a flange like this. So, the elbow is attached here. Other way of looking at this is something like a tap, almost looks like a tap. So, other way of looking at it is a tap through which water flows. Now, if you are not attaching to this elbow, if you are leaving this elbow alone and allowing water to flow, it will just keep moving. So, you have to fix. So, some force has to be exerted on this control volume, so to hold in place, and we are going to determine that. So, let us read that. Water flows steadily through the 90 degrees reducing elbow. 90 degrees tells the angle, reducing tells the reduction cross section area shown in the diagram. At the inlet of the elbow, the absolute pressure is 230 kilopascal. So, it is a different pressure, not atmospheric pressure. The cross section area is 0.01 meter squared. At the outlet, the cross section area is much smaller, it is 0.0025 meter squared, and the velocity is 16 meters per second. It is a high velocity there. The elbow discharges to the atmosphere. So, the pressure here at the outlet is atmospheric. We are asked to determine the force required to hold the elbow in place. Now, what is shown here is the control volume along with the control surface, and you have x direction flow here and the y direction flow here. Now, in this particular example, in addition to atmospheric pressure, we have one different pressure at the inlet, and that is what is shown in the second diagram here. The pressure force acting on the control surface. Everywhere you have atmospheric pressure. Here you have, in addition to atmospheric pressure, some extra pressure. So, that is why this arrow is bigger than the other arrows. Now, we have seen the last example, or you can intuitively understand that atmospheric pressure does not contribute to any net force. So, we can just subtract out the atmospheric pressure, and that is what is shown here, minus atmospheric pressure, and we can work out in terms of gauge pressure. So, in this diagram total pressure is shown, in the last diagram the gauge pressure is shown. What is the advantage? Everywhere it will be 0 in all the surfaces, only a region of inlet or outlet you will have to have a non-zero value. In terms of problem solving, becomes simpler. P1G represents the gauge pressure. Let us summarize this. So, pressure P1 on area A1 and pressure P atmosphere everywhere else, and it is given that here also the pressure atmospheric. Suppose if it is leaving a different pressure, then here also the arrow marks will be different of magnitude. And remember, all the pressures are shown as compressive, all are to acting on the control surface. No net force to atmospheric pressure. So, we subtract P atmospheric from the entire surface, work in gauge pressures, and then we are interested in this problem on the force of the flange on the control volume. It can have two components. In fact, we are going to solve for both the components in this example. In the earlier examples, we had only one of the components. In the case of plate, it was only Rx. In the case of balance, it was only Ry. So, we are slightly proceeding little involved example. So, we have both the components in this example, and so Rx, Ry are the components of force of the flange on the control volume, and like in the previous cases, we have taken them positive along the x axis and the y axis. So, the x axis and y axis are these directions, and Rx and Ry are taken positive along the axis. Then based on the sign we can interpret the physical significance. Now, let us find out the x direction force Rx, which means that we should write the momentum balance in the x direction. We consider the straight away the steady state momentum balance. with the convective term on the left hand side and the forces on the right hand side. Now, for the x momentum, inflow through section 1 alone contributes. So, I am replacing C s control surface with control surface 1 and integral of rho v x v dot and dA we have done few times. So, let us write the expression straight away, it is minus rho v 1 squared a 1, v x is v 1, it is along positive flow is along positive direction. So, v x is equal to positive v 1 and n is inflow. So, it is outward normal is along the negative x axis. So, n vector is minus I. So, if you substitute you get minus rho v 1 squared a 1. Of course, because it is inflow, this is negative, because it is along a positive axis, v x is positive, giving a negative sign. Now, let us look at the other forces. There is no body force along the x axis. Okay. Surface force, look at this, we have written in terms of the gauge pressure based on the discussion in the last slide into the area of this opening. So, P 1 g into A 1 and that acts, it is a compressive force, it acts onto the control volume. So, it acts along the positive x axis and that is why it is positive, plus we have our reaction force or x component of the reaction force, that is plus R x. So, both act along the same x direction, positive x axis. Okay. Now, we have this convective momentum in terms of v 1, but what we are given here is a velocity v 2 which was given as 16 meter per second. So, we do a mass balance, integral mass balance. So, this example in fact involves both integral mass balance and momentum balance. And now, the steady state integral mass balance is rho v dot and dA. Remember, for mass balance I will have to take into account the part of the control surface wherever mass crosses it. Okay. Only for the momentum balance we take only that part of the control surface through which for which we are writing the momentum balance, okay, or along which direction we are writing the momentum balance. So, here control surface here is split into control surface 1 and control surface 2. In the case of x momentum balance, we wrote control surface as control surface 1 because this flow in the y direction that does not contribute to the x direction force or x direction momentum balance. So, now we substitute this is inflow, this outflow, the negative sign and a positive sign. Okay. So, this becomes rho v 1 a 1 rho v 2 a 2. So, if we simplify we get v 1 a 1 is equal to v 2 a 2, something very well known to us. So, now we can find out what is the velocity v 1. We were given the area of the outflow and the outlet and the inlet, and this gives us 4 meters per second. Obviously, the area is reducing, at the leaving end is 16 meter per second, at the inlet end it is 4 meter per second. We would have straight away written this expression, but just to emphasize that that comes from a integral mass balance, we proceeded systematically and arrived at this expression. Okay. And you will also see that in the next example this v 1 a 1 will not be valid because we will be considering compressible flow. Okay. So, now we are ready with all the expressions. So, let us substitute in the x direction momentum balance. So, the convective momentum term was minus rho v 1 squared a 1, there was no body force and two contributions from surface forces, the gauge pressure and the reaction force. So, let us rewrite for the reaction force, x component of reaction force, and if we substitute 230 kilopascal was the absolute pressure, we need gauge pressure, subtract the atmospheric pressure, convert it to Pascal, always very much advisable to work in SI units, and this is the area of the inlet and density. We found out the velocity at the inlet 4 and it is 4 squared here, and the area is 0.01 giving us minus 1450 Newton. So, first observation is that the reaction force has two components, one due to the pressure and one due to the momentum of the incoming fluid, and you have the elbow here and fluid is entering and then the pressure. So, your force has to be in the opposite direction, not our force, meaning the force exerted by the flange. So, if you have a flange here, the flange has to exert a force along the negative x direction, that is why we get a negative sign here minus 1450. So, force due to pressure and momentum are along the towards the positive axis. So, the reaction force to hold the elbow should be along the negative x axis. So, the force exerted by the flange, because your flange is here, on the control volume is along the negative x axis, okay. Otherwise we will just keep moving towards the right. Okay. So, now coming to the y direction force, we write the integral balance of linear momentum along the y direction, and we neglect the weight if it is given, if it is available. If we are given the mass of the elbow, mass of water in the elbow, then we can include. In this particular example it is not given, sometimes may be negligible also, okay. So, we neglect that and so we have only convective momentum and the surface force on the right hand side. For the convective momentum, flow through the outlet alone, which is along the y direction, that alone contributes. So, I am replacing Cs with Cs2 and Vy is minus V2 because it is along the negative y axis. You have x along and y here, and the velocity is along the negative y axis. So, it is minus V2 and n is the outward normal, and so it is also along negative y axis. So, minus j vector. So, if you substitute in this expression, assume it is uniform, then you get minus rho V2 squared A2. Now, the surface force is only because of the y component of reaction force, there is no component due to pressure, okay. The gauge pressure is 0. Now, let us substitute in the integral balance and write it for the y component of the reaction force, which gives us minus rho V2 squared A2. Let us substitute the value. Now, the velocity is 16 meters per second and hence 16 squared. Area is small area 0.0025, giving us minus 640 Newton, okay. Now, this tells you that first observation, the y component of reaction is only because of momentum, okay. Now, how do you interpret this negative force? You have the elbow and then it is water is flowing, okay. Let us show the outlet of elbow alone. You have water flowing down, and because of that there is an upward thrust. Because water is flowing down, it exerts a upward thrust on the control volume or the elbow, which means that you should apply a force from the top, so that you hold the elbow, you supply a force opposite to the thrust, okay. So, just something like the launching of a rocket, okay. Because of the gases, of course high velocity and so on, there is a thrust on the rocket on the upward direction, and similarly here, because of water flowing outside the tap or this elbow, there is a upward force on the tap. So, the y component of the force exerted by the flange should be pointing downwards, okay. Otherwise you have something movement in the upward direction, that is the interpretation for this negative sign, okay. So, this example we have seen that the force finally apply will have some direction based on this Rx value and Ry value at both the components. Accordingly, you will have a direction for the net resultant force, okay.